Approximately 13.8 billion years ago, everything you have ever known, everything you have ever touched, everyone you have ever loved, every star you have ever seen, every galaxy spinning through the darkness, all of it existed in a space smaller than a single atom. That is not a metaphor. That is not poetic exaggeration. That is the actual scientific conclusion drawn from decades of observation, calculation, and theory. The entire observable universe, all 93 billion light-years of it, all 2 trillion galaxies, all the stars and planets and moons and asteroids and comets and gas clouds and black holes, everything that exists within the reach of our most powerful telescopes was once compressed into a point so small that calling it microscopic would be a vast overstatement. And here is the remarkable part. Here is the thing that keeps physicists awake at night and philosophers arguing in lecture halls. We do not actually know what happened at that moment. We cannot describe time zero. We have equations that work beautifully at 1/1,000,000,000th of a second after the beginning. We can trace the history of the cosmos with extraordinary precision from that impossibly early moment all the way to the present day. But the very instant of beginning, the actual moment of creation, if you want to call it that, remains hidden from us. Our mathematics breaks down, our physics fails, we hit a wall beyond which we cannot see. Let that sink in for a moment. The most important event in the history of everything, the event that made everything else possible, the event without which there would be no stars, no planets, no life, no you, remains fundamentally mysterious. We are like detectives who have reconstructed an entire crime scene with extraordinary detail, but cannot figure out who opened the door. Consider the scale of what we are discussing. If the entire observable universe were compressed to the size of a grain of sand, that grain would still be billions of times larger than what physicists believe the initial singularity might have been. The temperature at 1/1,000,000th of a second after the Big Bang was approximately 10 trillion degrees. To put that in perspective, the center of our sun burns at about 15 million degrees. The early universe was so hot that the core of the sun would feel like Antarctic winter by comparison. These numbers are so extreme that they lose all meaning to human intuition. We can write them down, we can calculate with them, but we cannot truly imagine them. If you tried to count to 13.8 billion, one number per second, without pausing for food or sleep or rest of any kind, you would be counting for approximately 437 years. That exceeds the lifespan of any human who has ever lived. It stretches back before the founding of most modern nations, and yet 13.8 billion years is merely the age of the universe, merely the time that has elapsed since this incomprehensible beginning. The timescales of the early universe are far shorter and far stranger. We will discuss events that happened in the first trillionth of a trillionth of a trillionth of a second. These numbers are so small that comparison fails entirely. You are made of material that was once compressed into that impossibly small point. The atoms in your hand, the calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it traces back to that moment. Not metaphorically, literally. The chain of cause and effect that led to your existence begins at the Big Bang and nowhere else. Every atom in your body has a history that stretches back 13.8 billion years to an event we still do not understand. Tonight, we are going to explore that event. We are going to travel back through time to the very edge of human knowledge, to the moment when our physics first starts to work, and then push even further into the realm of speculation and mystery. We will trace how the universe cooled and expanded, how the fundamental forces separated from their original unity, how matter emerged from pure energy, how the first atomic nuclei formed in a cosmic furnace that lasted only a few minutes. We will examine how light finally broke free to travel across space, creating the cosmic microwave background that we can still detect today. We will explore the evidence that convinced scientists the Big Bang actually happened. Evidence so compelling that it transformed cosmology from philosophy into precision science. And we will confront the mysteries that remain unsolved, the questions that challenge our deepest assumptions about reality itself. This will not be a story where we pretend to have all the answers. Science is comfortable with not knowing. In fact, Not knowing is where science begins. The honest truth is that our understanding of the Big Bang falls into three categories. There are things we know with tremendous confidence, supported by multiple independent lines of evidence. There are things we suspect but cannot prove, hypotheses that fit the data but remain unconfirmed. And there are things that remain completely mysterious, questions we do not even know how to approach with our current understanding of physics. We will explore all three categories tonight. The term Big Bang itself is somewhat misleading. It was coined in 1949 by the astronomer Fred Hoyle during a BBC radio interview. Hoyle was actually skeptical of the theory. He preferred a competing model called the steady-state theory, which proposed that the universe had no beginning and no end, that it simply existed eternally in more or less its current form. When Hoyle called the competing theory the Big Bang, he meant it dismissively. He was mocking the idea, but the name stuck, and now it is how everyone refers to the beginning of the universe. The problem is that the name suggests an explosion. It suggests a bang, a loud dramatic event, something bursting outward into pre-existing space. But that is not what happened. There was no sound because there was no medium for sound to travel through. There was no explosion into space because there was no space for anything to explode into. The Big Bang was not an explosion in space, it was an expansion of space itself. Space did not exist before the Big Bang. Time did not exist before the Big Bang. The Big Bang was the beginning of space and time together, woven into the fabric that physicists call space-time. Here is a mental model that might help. Imagine the surface of a balloon. Now imagine that the entire universe exists only on that surface. There is no inside of the balloon, no outside, just the two-dimensional surface. Now imagine inflating that balloon. Every point on the surface moves away from every other point. There is no center of the expansion on the surface itself. No matter where you stand on that balloon surface, everything else appears to be moving away from you. That is roughly how the expansion of the universe works. Except our universe has three spatial dimensions instead of two, and it is expanding through time as well. This means there is no location in space where the Big Bang happened. The Big Bang happened everywhere. Right where you are lying right now was once the center of an impossibly hot, dense universe. So was every other point in existence. The Big Bang was not an event that occurred at a particular place in space. It was an event that created space itself. Asking where the Big Bang happened is like asking where the North Pole is relative to the North Pole. The question does not make sense because it assumes a framework that does not apply. Similarly, asking what happened before the Big Bang may be a meaningless question. Albert Einstein showed us that space and time are not separate things. They are aspects of a single unified entity called space-time. If time itself began with the Big Bang, then asking what happened before is like asking what is north of the North Pole. There is no north of the North Pole. North is a direction on Earth's surface, and the North Pole is the point where that direction ceases to have meaning. Time might be similar. The Big Bang might be the point where time ceases to have meaning, where asking about before becomes incoherent. But we are not certain of this. Some physicists believe that time might extend backward beyond the Big Bang in ways we do not yet understand. Perhaps our universe arose from a previous universe that collapsed. Perhaps it budded off from a parent universe in some higher dimensional space. Perhaps time has always existed, but undergoes periodic transformations that look like beginnings. These are speculative ideas at the frontier of physics. We cannot test them with current technology, but they remain possibilities, reminders that the mystery of ultimate origins is far from solved. Why does any of this matter to you personally? Because you are not just observing the aftermath of the Big Bang, you are the aftermath of the Big Bang. Every atom in your body was processed through that cosmic furnace. The hydrogen atoms in your body, in the water that makes up most of your mass, are primordial. They have existed since the universe was about 3 minutes old. They have never been inside a star. They have never been part of any other structure. For 13.8 billion years, they have been drifting through the cosmos until, somehow, improbably, they ended up in you, the heavier elements, the carbon that forms the backbone of your DNA. the oxygen you breathe, the iron that makes your blood red, these were forged in the cores of stars that lived and died before our sun was born. But those stars themselves were made possible by the Big Bang. Their raw material came from those first 3 minutes. The astronomer Carl Sagan famously said that we are made of star stuff. That is true, but it does not go far enough. We are made of Big Bang stuff. We are made of singularity stuff. We are the universe organizing itself into a form that can wonder about its own origins. When you ask where the universe came from, you are the universe asking where it came from. This is not mysticism. This is the straightforward conclusion of physics and chemistry and biology. You are matter that has been processed through the Big Bang, through stellar furnaces, through planetary formation, through billions of years of evolution, until it reached a configuration that can contemplate its own history. Let us consider for a moment how recently we came to understand any of this. For most of human history, people had no idea that the universe had a beginning. The ancient Greeks debated whether the cosmos was eternal or created, but they had no way to settle the question observationally. Even into the early 20th century, many scientists assumed the universe had always existed in roughly its present form. The idea that everything began at a specific moment, that there was a first instant of time, seemed more like religion than science. The shift came gradually, then suddenly. In 1915, Einstein published his general theory of relativity, which described gravity not as a force, but as the curvature of space-time caused by mass and energy. His equations allowed, for the first time, a mathematical description of the universe as a whole. To Einstein's discomfort, his equations suggested that the universe could not be static. It had to be either expanding or contracting. Einstein himself found this implication so disturbing that he added a term to his equations, the cosmological constant, specifically to allow for a static universe. He later called this the biggest blunder of his career. In 1929, the astronomer Edwin Hubble made observations that changed everything. Using the 100-inch telescope at Mount Wilson Observatory, Hubble measured the distances to nearby galaxies and found that nearly all of them were moving away from us. Moreover, the farther away a galaxy was, the faster it was receding. This relationship, now called Hubble's law, was exactly what you would expect if space itself were expanding. The universe was not static after all. It was growing, stretching, carrying galaxies along with it like dots on an inflating balloon. If the universe is expanding now, it must have been smaller in the past. Run the clock backward far enough, and everything must have been compressed together. The logic was inescapable. The universe had a beginning. It started from an incredibly hot, dense state and has been expanding and cooling ever since. This was the birth of modern cosmology, the transformation of speculation into science. The Big Bang was not a philosophical hypothesis. It was a prediction that could be tested, a theory that made specific claims about what we should observe if it were true. Let us begin our journey through that history. We will start at the very edge of knowable time, at the moment when our equations first begin to work, and move forward through the universe's earliest epochs. The numbers will be strange. The conditions will be impossible to truly imagine, but the story itself is the greatest story ever told. The story of how everything came to be. Get comfortable. Take a deep breath. This will be a long journey through some of the deepest questions humans have ever asked about the cosmos we inhabit. The cosmic timeline we are about to explore spans an almost incomprehensible range. We will discuss events that happened in the first trillionth of a trillionth of a trillionth of a second, and events that happened hundreds of millions of years later. We will encounter temperatures that make the centers of stars seem cold, and temperatures colder than anything in the present-day universe. We will watch as the fundamental forces of nature separate from their original unity, as matter condenses from pure energy, as the first atoms form, as light breaks free to travel across the cosmos. Each stage of this journey reveals something profound about the universe we inhabit and about our place within it. The earliest moment we can describe with any confidence is called the Planck epoch. It ended at approximately 10 to the negative 43 seconds after the beginning. That number is so small that it defies comprehension. There are more Planck times in a single second than there have been seconds since the Big Bang. There are more Planck times in the blink of an eye than there are atoms in the observable universe. At the end of the Planck epoch, the universe was already unimaginably old by the standards of those first moments. Even though less than a trillionth of a trillionth of a trillionth of a trillionth of a second had passed. Before the end of the Planck epoch, at even earlier times, our physics breaks down completely. We cannot say what happened. We cannot say if anything happened. We cannot say if the word happened even has meaning in that context. The Planck epoch represents a wall beyond which our current understanding cannot penetrate. But from the end of that epoch forward, we can trace the evolution of the universe with increasing confidence and precision. The story we are about to tell is one of the great achievements of human knowledge, pieced together from observations of the most distant objects in the universe, from experiments in the most powerful particle accelerators ever built, from mathematical theories that push the limits of human abstraction. It is a story still incomplete, still full of mysteries, but more detailed and more confirmed than anyone a century ago could have imagined. So let us begin at that wall, at the edge of the knowable, and journey forward through the birth of everything. Let the numbers wash over you. Let the ideas settle into your mind like sediment drifting to the bottom of a still pond. We are in no hurry. The universe is patient, and tonight, so are we. The Planck epoch ended at 10 to the negative 43 seconds after the Big Bang. This moment marks the earliest boundary of our physics, the point beyond which our equations cease to produce meaningful results. Before this instant, in the unimaginably brief sliver of time between 0 and 10 to the negative 43 seconds, we simply do not know what happened. Our two greatest theories of physics, general relativity and quantum mechanics, both apply to conditions that extreme, but they contradict each other. They give different answers to the same questions. They cannot both be right, and we do not know which one to trust. So we are left with a wall, a hard limit to human knowledge that may or may not be permanent. To understand why this wall exists, you need to understand something about how physics works. We do not have one unified theory of everything. We have two separate frameworks that each work brilliantly in their own domain but refuse to play nicely together. General relativity, Einstein's masterpiece, describes gravity and the large-scale structure of the universe. It tells us how planets orbit stars, how galaxies form, how black holes warp space and time. General relativity works perfectly for anything large and massive. Quantum mechanics, developed in the early 20th century by Planck, Bohr, Heisenberg, Schrödinger, and many others, describes the behavior of atoms, subatomic particles, and the forces that govern them. It explains why atoms are stable, how light interacts with matter, how particles can exist as probability waves until they are observed. Quantum mechanics works perfectly for anything small, but at the Planck epoch, both frameworks apply simultaneously. The universe was so small that quantum effects dominated, but it was so dense that gravity was enormously strong. You need both theories at once, and they give contradictory instructions. It is as if you had two manuals for operating the same machine. Manual A says turn the dial left. Manual B says turn the dial right. Both manuals have worked perfectly every time you have consulted them separately. But now you need to use both at once, and they disagree. Physics does not know which instruction to follow. This is not merely a gap in our knowledge that will be filled in by more careful experiments. It represents a fundamental incompatibility in our understanding of nature. We need what physicists call a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics into a single coherent picture. Many brilliant people have worked on this problem for decades. String theory is one approach. Loop quantum gravity is another. There are others. None of them has been confirmed by experiment. None of them has gained universal acceptance. The unification of quantum mechanics and gravity remains one of the greatest unsolved problems in all of physics. So when we ask what happened before the Planck epoch, the honest answer is that we do not know, and we may never know. Our instruments cannot probe that era. Our mathematics breaks down. The wall may be temporary, something that will fall once we develop better theories. Or it may be permanent, a fundamental limit to what can ever be known about the ultimate origin of things. What we think we know about conditions at the Planck epoch is speculative but fascinating. Physicists believe that at those extreme temperatures and densities, the four fundamental forces of nature were unified. They were not four separate forces, but one single force behaving in one single way. As the universe cooled, this unity broke apart. The forces separated one by one, like a liquid freezing into different kinds of crystals, depending on local conditions. Understanding this unification and separation is key to understanding the very early universe. Let me tell you about these four forces, because they are the scaffolding on which everything is built. Every interaction you have ever experienced, every sensation, every movement, every thought, ultimately reduces to some combination of these four fundamental forces. They are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each one has its own character, its own strengths and weaknesses, its own domain of influence. Together they account for everything that happens in the physical universe. Gravity is the most familiar force. It is what keeps your feet on the ground, what keeps the Earth orbiting the sun, what keeps galaxies from flying apart. Gravity is the sculptor of large-scale structure in the universe. But here is the surprising thing. Gravity is by far the weakest of the four forces. It is about 10 to the 36 times weaker than electromagnetism. That is a 1 followed by 36 zeros times weaker. The only reason gravity seems strong to us is that it is always attractive and it has unlimited range. Electric charges can be positive or negative and tend to cancel out over large distances. But mass is always positive and always attracts other mass. So gravity accumulates over cosmic distances. Across vast amounts of mass, it becomes the dominant force. We describe gravity beautifully using Einstein's general relativity. Mass and energy curve spacetime, and objects follow the straightest possible paths through that curved geometry. This is why planets orbit stars, and why light bends around galaxies. General relativity has been tested to extraordinary precision and has never failed. But at the quantum level, we do not know how gravity works. We do not have a quantum theory of gravity that makes consistent predictions. This is the root of the Planck epoch problem. Electromagnetism is the force behind light, electricity, magnetism, and chemistry. It is why atoms bond together to form molecules. It is why you do not fall through your chair. When you sit down, the electrons in your body repel the electrons in the chair, preventing you from passing through. Every chemical reaction, every biological process, every signal in your nervous system, all of it runs on electromagnetism. This force is much stronger than gravity, but can be either attractive or repulsive, depending on the charges involved. Unlike gravity, we understand electromagnetism at the quantum level. The theory is called quantum electrodynamics, and it is the most precisely tested theory in all of science. Its predictions match experiments to more than 10 decimal places. The strong nuclear force is what holds atomic nuclei together. Protons are positively charged. Left to themselves, electromagnetism would cause them to fly apart. But the strong force overpowers electromagnetism at short distances, binding protons and neutrons together in the nucleus. The strong force is about 100 times stronger than electromagnetism, but it has an extremely short range, only about 10 to the negative 15 meters. Beyond that distance, it essentially does not exist. The strong force also holds quarks together inside protons and neutrons. Quarks are the fundamental building blocks of nuclear matter, and they are permanently confined by the strong force. You cannot isolate a single quark. Try to pull two quarks apart, and the energy you invest creates new quark pairs. This property is called confinement, and it is one of the strangest features of the subatomic world. The weak nuclear force is responsible for certain kinds of radioactive decay. It can transform one type of particle into another, turning a neutron into a proton, for example. The weak force is crucial for the processes that power the sun. Without it, hydrogen could not fuse into helium, and stars could not shine. The weak force has the shortest range of all, only about 10 to the negative 18 meters. It was unified with electromagnetism in the 1960s and 70s. At high enough energies, they become aspects of a single electroweak force. This unification was one of the great triumphs of 20th century physics and earned multiple Nobel Prizes. Now here is the grand picture. At the Planck epoch, all four forces were one. There was no distinction between gravity and electromagnetism, between the strong force and the weak force. They were all aspects of a single unified interaction. As the universe cooled, this unity broke apart through a series of phase transitions, similar to water vapor condensing into liquid and then freezing into ice. First, gravity separated from the other three forces. Then the strong force separated. Finally, electromagnetism and the weak force split apart. Each separation released enormous amounts of energy and fundamentally changed the character of the universe. We believe gravity separated first, at the end of the Planck epoch, but we cannot describe this separation mathematically because we do not have a quantum theory of gravity. We can describe the later separations, particularly the electroweak transition, with much more confidence. The electroweak unification has been confirmed experimentally. We have detected the particles that carry the electroweak force and measured their properties. The pattern matches our theories. But the earlier unifications, the ones involving gravity and the strong force, remain theoretical. We have good reasons to believe they occurred, but we have not directly observed them. The Planck epoch takes its name from Max Planck, the German physicist who discovered the quantum nature of energy in 1900. The Planck scale refers to the smallest meaningful units of length, time, and energy that we can define using fundamental constants. The Planck length is about 10 to the negative 35 meters. The Planck time is about 10 to the negative 43 seconds. Below these scales, our current physics loses all meaning. Space and time themselves may not exist in any recognizable form. The Planck epoch is the era when the universe was smaller than these scales, when our concepts of space and time become questionable. Some physicists believe that space and time are not fundamental. They may emerge from something deeper, the way temperature emerges from the motion of molecules. A single molecule does not have a temperature. Temperature is a collective property that emerges when many molecules interact. Similarly, space and time might be collective properties that emerge from some underlying quantum reality. At the Planck scale, that underlying reality might be directly relevant. Space might not be smooth and continuous. It might be granular, made of tiny discrete chunks. Time might not flow uniformly. It might freeze or jump, or cease to have meaning. Loop quantum gravity is one approach to these questions. It suggests that space is made of tiny loops or nodes, discrete quanta of geometry, with a minimum size of about the Planck length. At ordinary scales, these quantum effects average out and space appears smooth. But at the Planck epoch, space was only a few quanta across. The Big Bang might not have been a true singularity in this picture. It might have been a quantum bounce, a transition from a previous contracting phase to the current expanding one. The universe might be cyclic, oscillating between expansion and contraction forever. String theory is another approach. It suggests that what we perceive as point-like particles are actually tiny vibrating strings of energy. Different vibrational modes correspond to different particles. String theory requires extra dimensions beyond the three of space and one of time that we experience. These extra dimensions might be curled up so small that we cannot detect them, or they might extend infinitely in directions we cannot perceive. In some versions of string theory, our entire universe is a three-dimensional membrane floating in a higher dimensional space. The Big Bang might have been a collision between membranes, a violent meeting of universes that created everything we know. These are speculative ideas. They are not established science. We have no experimental evidence for extra dimensions, for cosmic bounces, for membrane collisions. But they are ideas that serious physicists take seriously. Ideas that follow from attempting to extend our knowledge beyond the Planck wall. They remind us that what we do not know is vast, that our current understanding may be only a small piece of a much larger picture. General relativity. When applied to the Big Bang, predicts a singularity at time zero. A singularity is a point where physical quantities become infinite. The density becomes infinite. The temperature becomes infinite. The curvature of space-time becomes infinite. Infinities in physics are almost always a sign that something has gone wrong with your theory. They indicate that you are applying equations outside their domain of validity. The singularity at the Big Bang is probably not a real physical state. It is probably an artifact of using general relativity, where general relativity does not apply. A correct quantum theory of gravity would presumably resolve the singularity into something finite and comprehensible, but we do not have that theory yet. What might have caused the Big Bang? This question assumes that causation makes sense when applied to the beginning of time itself. If time began with the Big Bang, then there was no before in which a cause could operate. The question might be meaningless, like asking what is north of the North Pole, but it might not be meaningless. Our intuitions about causation evolved in a world of time and change. They might not apply to the origin of time and change themselves. Or they might apply in ways we have not yet imagined. Some physicists have proposed that the universe is a quantum fluctuation from nothing. In quantum mechanics, particles can briefly pop into existence and then disappear again, borrowing energy from the vacuum for a fleeting moment. Perhaps the entire universe is such a fluctuation, one that happened to be large enough and long-lasting enough to become self-sustaining. This idea has mathematical support, but raises profound philosophical questions. What is the nothing from which the universe fluctuated? Is nothing a something? Can quantum mechanics operate in the absence of space and time? Other physicists have proposed that our universe budded off from a parent universe. Perhaps black holes give birth to new universes. Perhaps cosmic inflation spawns infinite pocket universes. Perhaps we are one branch of an eternally self-reproducing multiverse. These ideas are fascinating, but may be permanently untestable. If other universes exist but cannot communicate with ours, how could we ever know? The boundary between physics and metaphysics becomes blurry at these extremes. We may simply have to accept that some questions have no answers, not because we are not smart enough to find them, but because the questions themselves are malformed. Why is there something rather than nothing? What caused the first cause? What came before the beginning? These questions assume frameworks that may not apply at the deepest levels of reality. Learning to recognize malformed questions may be as important as finding answers to well-formed ones. The Planck epoch represents humanity's current horizon of ignorance. Beyond it lies terra incognita, unmapped territory where our physics cannot guide us. But this horizon is not fixed. A century ago, we could not describe the first second after the Big Bang with any confidence. Now we can describe the first trillionth of a second. Progress has been extraordinary. The wall has been pushed back by the accumulation of theory and experiment over decades. Perhaps it will continue to retreat. Perhaps we will eventually understand the Planck epoch itself and push into whatever lies beyond. Or perhaps we will discover that the wall is fundamental, that some aspects of ultimate origins are forever closed to human investigation. Either outcome would be profound. To understand the beginning would be to complete the greatest project of human knowledge. To prove it unknowable would be to discover a fundamental limit of the human mind. Both possibilities deserve our wonder and our humility. For now, we stand at the wall and peer into the darkness beyond. We know that something happened there. We know that whatever happened gave rise to everything that followed. We know that the rules were different, that our familiar forces were unified, that space and time themselves may have been in flux, but the details remain hidden. The Planck epoch guards its secrets behind the breakdown of our equations. Let us turn away from the wall now and follow the universe forward through time. From the end of the Planck epoch, our physics begins to work. The story becomes clearer, more detailed, more confident. We can trace the separation of forces, the appearance of particles, the formation of the first nuclei. The mysteries do not disappear entirely, but they become more tractable. The wall recedes behind us as we journey forward into the hot, dense, rapidly expanding universe of the first second. The temperature at the end of the Planck epoch was about 10 to the 32 degrees Kelvin. That is a 1 followed by 32 zeros. It is a number so large that comparison fails. The center of the hottest stars reaches only about 1 billion degrees. The early universe was 100 trillion trillion times hotter than that. At such temperatures, matter as we know it could not exist. Atoms would be torn apart instantly. Even protons and neutrons would be dissolved into their constituent quarks. Everything existed as a seething plasma of elementary particles, energy, and radiation, all thoroughly mixed together in a state of unimaginable chaos. And yet, from this chaos, order would emerge. The forces would separate. Particles would form. Nuclei would assemble. Atoms would coalesce. Stars would ignite. Galaxies would gather. And eventually, after billions of years of patient evolution, consciousness would arise to look back at its own origins with wonder and perplexity. The story of how that happened, the story of cosmic evolution from the Planck epoch to the present, is what we continue to explore. The wall is behind us now. The universe lies ahead, cooling and expanding into the forms we will come to recognize. Let us follow it forward. The universe had a problem. Actually, it had several problems, and they were serious enough to make physicists question whether they understood anything at all about the first moments of cosmic history. These problems did not emerge from a lack of evidence. They emerged from too much evidence pointing in directions that seemed impossible. The universe we observe today has properties that should not exist if the Big Bang happened the way we initially thought it did. Something was missing from the story. Something dramatic must have happened in the first fraction of a second that we had not accounted for. The first problem is called the horizon problem, and it concerns the strange uniformity of the cosmos. When you look at the cosmic microwave background, the faint glow of radiation left over from when the universe became transparent about 380,000 years after the Big Bang, you find something remarkable. The temperature of this radiation is almost exactly the same in every direction. It varies by only about 1 part in 100,000. That might sound like a reasonable amount of variation, but think about what it implies. Regions of space on opposite sides of the sky. Regions that are now separated by tens of billions of light years, somehow have almost exactly the same temperature. They have the same density. They have the same properties to extraordinary precision. But here is the puzzle. Those regions have never been in contact with each other. Light has not had time to travel between them since the beginning of the universe. Information cannot travel faster than light. So how did those regions coordinate? How did they agree to have the same temperature if they have never communicated? Imagine walking into a room containing 1,000 people who have never met, who have never spoken to each other, who have no common history, and every single one of them is wearing the exact same outfit, down to the smallest detail. Same color, same style, same size, same accessories. This would be incredibly strange. You would immediately suspect that something happened before they entered the room, some prior contact that explains the coordination. The horizon problem is exactly this puzzle, on a cosmic scale. The universe looks coordinated across distances that should preclude any coordination. The second problem is called the flatness problem, and it concerns the geometry of space. Einstein showed us that mass and energy curve space-time. A universe filled with matter should have curved geometry. It could be positively curved, like the surface of a sphere, where parallel lines eventually meet and the angles of a triangle add up to more than 180 degrees. It could be negatively curved, like a saddle, or the surface of a trumpet, where parallel lines diverge and triangles have angles summing to less than 180 degrees. Or it could be flat, like an infinite tabletop, where parallel lines stay parallel forever and triangles have angles summing to exactly 180 degrees. When we measure the geometry of our universe, we find that it is flat, not approximately flat, not sort of flat. Flat to extraordinary precision, within about 1% of perfect flatness and possibly much closer. This might seem like good news, but it is actually deeply puzzling. A flat universe requires an incredibly precise balance between the amount of matter and energy in the universe and the rate of expansion. The density must equal a particular critical value to extraordinary precision. If the density was slightly higher, the universe would have collapsed back on itself long ago. If it was slightly lower, matter would have dispersed so quickly that no galaxies could ever have formed. The universe has apparently been balancing on a knife edge for 13.8 billion years. To appreciate how strange this is, imagine balancing a pencil on its point. If you could somehow set it exactly vertical, it would theoretically stay balanced, but the slightest perturbation would send it toppling. The flat universe is like a pencil that has been balanced on its point for billions of years without falling. Either we are incredibly lucky, or something set up the initial conditions with extraordinary precision. Or something happened early on that drove the universe toward flatness, regardless of how it started. The third problem is called the monopole problem, and it involves particles that should exist but do not. When physicists developed theories that unified the strong nuclear force with the electro-weak force, these grand unified theories predicted the existence of magnetic monopoles. A monopole is a particle with only a north magnetic pole or only a south magnetic pole. Unlike ordinary magnets, which always have both, the mathematics of grand unification essentially requires monopoles to exist. And the conditions of the early universe, when the forces were unified and then separated, should have produced monopoles in enormous quantities. The universe should be swimming in them. But we have never found a single magnetic monopole. Despite decades of searching with increasingly sensitive experiments, not one has ever been detected. If they were created in the early universe, as grand unified theories predict, where did they go? Why is the universe not filled with these particles that physics says must have been produced? The story of how these problems were solved is itself a remarkable tale of scientific serendipity. In the late 1970s, a young postdoctoral researcher named Alan Guth was struggling to find a permanent position in academia. He had bounced between several universities, working on particle physics problems that seemed disconnected from cosmology. His career was uncertain. His future was unclear. He was not trying to revolutionize our understanding of the universe. He was simply trying to solve a technical puzzle about magnetic monopoles. Guth had been working with a colleague named Henry Tye on grand unified theories, the mathematical frameworks that attempt to describe how the strong nuclear force unifies with the electro-weak force at extremely high energies. These theories made a troubling prediction. They said that the early universe should have produced enormous numbers of magnetic monopoles, hypothetical particles carrying isolated north or south magnetic poles. The problem was obvious. If monopoles had been produced in the quantities these theories predicted, they should be everywhere. The universe should be swimming in them. Yet despite decades of searching, no one had ever found a single magnetic monopole. Something was wrong. On the evening of December 6, 1979, Guth was working late in his office at the Stanford Linear Accelerator Center. He was thinking about the monopole problem, scribbling equations, trying to find a way out. And then it hit him. What if there had been a period of extremely rapid expansion in the very early universe? What if space had stretched so dramatically that any monopoles produced before or during this expansion were diluted to essentially zero density? The monopoles would still exist in principle, but they would be spread so thin across such an enormous volume that we would never encounter one. Guth immediately recognized that this idea, which he would soon call inflation, solved more than just the monopole problem. It also explained the horizon problem and the flatness problem. He was so excited that he wrote in his notebook, in capital letters, "Spectacular realization." Those words, preserved in his original notes, mark one of the great eureka moments in the history of physics. Guth had not set out to explain the origin of cosmic structure or the uniformity of the universe. He had stumbled onto these explanations while trying to solve an entirely different puzzle. This is how science often works. The biggest discoveries come not from direct assault on the biggest questions, but from following smaller threads that unexpectedly lead to profound insights. The mathematics of inflation involves concepts that challenge everyday intuition. Exponential growth is fundamentally different from the linear growth we experience in daily life. If something grows linearly, it adds the same amount in each time interval. A tree might grow 1 foot per year, adding 1 foot, then another foot, then another. After 10 years, it has grown 10 feet. But if something grows exponentially, it multiplies by the same factor in each time interval. Something that doubles every time interval grows from 1 to 2 to 4 to 8 to 16 to 32. After just 20 doublings, it has grown by a factor of more than 1,000,000. After 40 doublings, more than 1,000,000,000. After 60 doublings, more than 1,000,000,000,000. During inflation, the universe doubled in size roughly every 10 to the negative 37 seconds. That timescale is so short that human language fails to describe it. In each of those intervals, the universe doubled, then doubled again, then doubled again. Perhaps 80 or 90 doublings occurred before inflation ended. The cumulative effect was an expansion by a factor of at least 10 to the 26, possibly much more. A region smaller than a proton became larger than the entire observable universe is today. This all happened in about 10 to the negative 32 seconds, a duration so brief that even calling it instantaneous seems like an overstatement. How does this solve the horizon problem? Before inflation, the entire observable universe was far smaller than an atom. It was small enough that all parts of it were in contact with each other. Light had plenty of time to travel from one end to the other. Temperature equalized, density smoothed out. Everything reached a state of thermal equilibrium. Then inflation happened. That tiny uniform region was stretched to cosmic scales almost instantaneously. The uniformity we see today is not because distant regions somehow coordinated after the Big Bang. It is a fossil of their ancient contact before inflation tore them apart. The universe looks the same everywhere because it was once small enough for everywhere to be the same place. How does inflation solve the flatness problem? Imagine a balloon. When the balloon is small, you can easily see that its surface is curved. The curvature is obvious. Now imagine inflating that balloon to an enormous size, far larger than the Earth. If you stood on its surface at that point, it would look flat to you. The curvature would still exist mathematically, but it would be so gentle, stretched over such a vast scale, that any local region would appear perfectly flat. Inflation did this to the universe. Whatever curvature existed before inflation was stretched out by the enormous expansion. The universe became flat, not because it started flat, but because inflation made any initial curvature negligible. A universe that starts with almost any geometry will end up flat after sufficient inflation. How does inflation solve the monopole problem? Monopoles were indeed created in the early universe, just as grand unified theories predict, but they were created before inflation. When inflation occurred, it diluted them. Imagine taking a handful of sand and spreading it across a surface the size of a continent. The sand grains would be so sparse that you would never find one. Inflation did this to monopoles. The same number of monopoles now occupy a vastly larger volume. The density dropped to essentially zero. There might be only one monopole in the entire observable universe. We would never find it. The monopoles are still out there in principle, but inflation made them irrelevant. Inflation solves these three problems elegantly, but its implications go far beyond problem solving. Inflation makes a prediction that is nothing short of astonishing. It says that the quantum fluctuations that exist in all fields, the tiny random variations that are intrinsic to the quantum nature of reality, were stretched by inflation to cosmic scales. These fluctuations became the seeds of all structure in the universe. In quantum mechanics, empty space is not truly empty. It seethes with tiny fluctuations, particles and antiparticles popping into existence and annihilating, fields randomly varying from point to point. These fluctuations are normally inconceivably small, relevant only at subatomic scales, but during inflation, they were stretched. A fluctuation that was smaller than a proton became larger than a galaxy. The randomness of quantum mechanics was imprinted on the universe at the largest scales. The regions that were slightly denser due to these fluctuations became the seeds of galaxies. Gravity amplified these small differences over billions of years. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their neighbors, becoming emptier. The cosmic web of filaments and voids that we see today, the distribution of galaxies across billions of light years, all of it traces back to quantum fluctuations during inflation. The pattern of hot and cold spots in the cosmic microwave background, the 1 part in 100,000 variations we mentioned earlier, matches the pattern predicted by inflated quantum fluctuations. We can literally see the stretched-out quantum randomness of the early universe written across the sky. This is perhaps the most profound implication of inflation. The largest structures in the universe, clusters of galaxies spanning hundreds of millions of light years, originated from the smallest possible fluctuations, quantum effects at scales far below atomic. Inflation bridges quantum mechanics and cosmology in a way that no other theory does. It connects the physics of the very small to the structure of the very large. Your own existence traces back to a quantum fluctuation that occurred 10 to the negative 36 seconds after the Big Bang. The galaxy you live in, the solar system that contains Earth, the atoms in your body, all of it exists because of randomness at the quantum level that inflation promoted to cosmic significance. The physical mechanism that drove inflation remains mysterious. Physicists hypothesize a scalar field called the inflaton that permeated space during this era. A scalar field is the simplest kind of field, one that has a value at every point in space but no direction. Temperature is an everyday example of a scalar field. At every point in a room, there is a temperature, a single number with no direction attached. The inflaton field was similar, a number at every point in space, but its properties were extraordinary. The inflaton field had potential energy, energy stored in its configuration like energy stored in a compressed spring. When the field was in its high energy state, this potential energy behaved like negative pressure. In Einstein's general relativity, pressure contributes to gravity. Positive pressure attracts, but negative pressure repels. The inflaton field's negative pressure pushed space apart, causing the exponential expansion. The field was like a compressed spring, driving the universe outward, except the spring was made of space itself. At some point, the inflaton field rolled down from its high energy state to a lower energy state, like a ball rolling down a hill. When it reached the bottom, inflation ended. The potential energy that had been driving the expansion was released, converting into the particles and radiation that filled the post-inflationary universe. This process, called reheating, produced the hot, dense state that we normally associate with the Big Bang. In a sense, what we call the Big Bang, the hot beginning of the universe, was actually the end of inflation rather than the absolute beginning of everything. Different models of inflation propose different shapes for the potential energy hill that the inflation rolled down. Some models have a steep hill, producing brief inflation. Others have a gentle slope, producing prolonged inflation. Some have multiple valleys, allowing the field to get stuck temporarily before continuing its descent. The specific shape of the potential determines the details of inflation, including how long it lasted, how much the universe expanded, and what patterns it left in the cosmic microwave background. By studying the microwave background in exquisite detail, cosmologists can constrain which models are viable and which are ruled out by observation. One of the most mind-bending implications of inflation is eternal inflation. In many models, inflation does not end everywhere at once. It ends in some regions, which become universes like ours, but continues in others. The regions where inflation continues keep expanding exponentially, spawning new regions where inflation ends, which spawn more regions where it continues. This process might never stop. The result would be an infinite multiverse, a foam of pocket universes, each one potentially having different physical properties, most of them forever inaccessible to each other. If eternal inflation is correct, our observable universe is just one bubble in an infinite sea of bubbles. Beyond our cosmic horizon, space might still be inflating, creating new universes at an ever-accelerating rate. We could never reach these other universes. We could never communicate with them. We could never even confirm that they exist. But their existence would follow logically from the same theory that explains the flatness and uniformity of our own cosmos. The price of explaining what we see might be accepting the existence of infinitely much that we can never see. This is speculative. Eternal inflation is not established science. It is a theoretical possibility that follows from certain versions of inflation theory. Some physicists embrace it as a natural consequence of our best models. Others reject it as unfalsifiable and therefore unscientific. The debate continues. But the very fact that we are having this debate, that our theories of the first fraction of a second lead to questions about infinite multiverses, shows how far our understanding has come and how much further it might yet go. We have indirect evidence that inflation occurred. The cosmic microwave background shows patterns that match inflationary predictions remarkably well. The flatness of the universe, the uniformity of the cosmos, the absence of monopoles, all fit the inflationary picture. But we have not directly detected the inflation field. We have not observed the primordial gravitational waves that inflation should produce. Future experiments may detect these waves, providing more direct evidence for inflation, or they may fail to find them, forcing us to revise our theories. The universe emerged from inflation, transformed. The exponential expansion had smoothed and flattened space to extraordinary precision. The quantum fluctuations had been stretched to cosmic scales, seeding the structure that would eventually become galaxies. The energy of the inflation field had been converted into particles, filling the universe with a hot, dense plasma. And the clock was ticking toward the next phase of cosmic evolution, the era of particle physics, when the fundamental forces would finish separating and matter would condense from pure energy. That is where our journey continues. The universe was now a seething cauldron of energy and particles, hotter than anything that exists in the cosmos today, denser than the cores of neutron stars. Inflation had ended. The inflation field had surrendered its energy, converting it into the fundamental particles and radiation that would become everything we know. The temperature was approximately 10 to the 27 degrees Kelvin, a number so enormous that comparison becomes absurd. At this temperature, matter as we know it could not exist. Atoms were impossible. Even protons and neutrons were impossible. Everything was dissolved into its most elementary constituents, a plasma of quarks and leptons and gauge bosons, all careening through space at nearly the speed of light, colliding constantly, creating and annihilating in an endless frenzy. This state of matter is called a quark-gluon plasma. Quarks are the fundamental building blocks of protons and neutrons. Each proton contains 3 quarks, 2 up quarks, and 1 down quark, bound together by the strong nuclear force. Each neutron also contains 3 quarks, 2 down quarks, and 1 up quark. Under normal conditions, quarks are permanently confined inside these composite particles. You cannot isolate a single quark no matter how hard you try. The strong force has a peculiar property. Unlike gravity or electromagnetism, which weaken with distance, the strong force actually gets stronger as you try to pull quarks apart. Eventually, you invest so much energy trying to separate them that the energy converts into new quark-antiquark pairs. You end up with more confined quarks rather than free ones. But in the early universe, the temperature was so extreme that this confinement broke down. Quarks roamed freely through space, not bound into protons or neutrons or anything else. The gluons that normally mediate the strong force-filled space like a thick soup. Everything was mixed together in a state that had not existed since the beginning of time and would never exist again until humans recreated it briefly in particle accelerators, billions of years later. At facilities like the relativistic heavy ion collider in New York and the Large Hadron Collider in Switzerland, physicists have smashed gold nuclei and lead nuclei together at nearly the speed of light. For the briefest instant, they create tiny fireballs of quark-gluon plasma, droplets of the early universe materializing in laboratories on Earth. These experiments have confirmed many of our theories about this exotic state of matter. The early universe really was filled with freely roaming quarks. Our equations are not just speculation. They describe something real. Let us spend more time with the particles themselves, the cast of characters in the drama of the early universe. The Standard Model of Particle Physics, developed over the second half of the 20th century and confirmed by countless experiments, describes all known fundamental particles and 3 of the 4 fundamental forces. It is one of the most successful theories in the history of science, making predictions that have been verified to extraordinary precision. Understanding the Standard Model is essential to understanding what happened in the first second after the Big Bang. The particles of the Standard Model fall into 2 broad categories. Fermions are the particles that make up matter. Bosons are the particles that carry forces. This distinction reflects a deep property of quantum mechanics related to spin, the intrinsic angular momentum that particles carry. Fermions have half-integer spin and obey the Pauli exclusion principle, which says that no 2 identical fermions can occupy the same quantum state. This is why electrons in atoms arrange themselves into shells rather than all piling into the lowest energy state. Bosons have integer spin and can pile up without restriction. This is why laser light, made of photons which are bosons, can be coherent, with countless photons all in exactly the same state. The fermions divide further into quarks and leptons. Quarks feel the strong nuclear force, leptons do not. There are 6 types of quarks, called flavors, arranged in 3 generations. The first generation contains the up quark and the down quark, the constituents of protons and neutrons. The up quark has an electric charge of positive 2/3. The down quark has a charge of negative 1/3. A proton contains 2 up quarks and 1 down quark, giving it a total charge of positive 1. A neutron contains 2 down quarks and 1 up quark, giving it a total charge of 0. The second generation of quarks contains the charm quark and the strange quark. The third generation contains the top quark and the bottom quark. These heavier quarks are unstable. They decay rapidly into first-generation quarks. The top quark is the heaviest known fundamental particle, with a mass about 175 times that of a proton. It was not discovered until 1995 at the Tevatron Accelerator in Illinois, because producing it requires enormous energies. The top quark decays so quickly that it never forms bound states with other quarks. It is gone before it can feel the confining effects of the strong force. The leptons also come in 3 generations. The first generation contains the electron and the electron neutrino. Electrons are familiar from chemistry and everyday electricity. They carry a charge of -1 and have a mass about 1836 times smaller than a proton. Electron neutrinos are ghostly partners, produced in radioactive decays and nuclear reactions, carrying no electric charge and interacting only through the weak force and gravity. Billions of neutrinos pass through your body every second without interacting with anything. The second generation of leptons contains the muon and the muon neutrino. Muons are heavier cousins of electrons, about 207 times more massive, but otherwise identical in their interactions. They are unstable, decaying into electrons in about 2 microseconds. The third generation contains the tau lepton and the tau neutrino. Tau particles are even heavier, about 3,477 times the mass of an electron, and decay even more rapidly than muons. Why are there 3 generations of fermions? Why not 1, or 2, or 17? We do not know. The Standard Model does not explain the number of generations. It simply describes what we observe. The pattern of 3 generations, with each generation heavier and less stable than the one before, suggests some deeper structure that we have not yet discovered. This is one of the many hints that the Standard Model, successful as it is not the final word in particle physics. The bosons are equally remarkable. The photon carries the electromagnetic force. It is massless and travels at the speed of light. It is its own antiparticle. Every electromagnetic interaction, from the light entering your eyes to the chemistry holding your molecules together, is mediated by photon exchange. When 2 electrons repel each other, they are exchanging virtual photons, quantum fluctuations that carry the electromagnetic force between them. The W and Z bosons carry the weak nuclear force. Unlike the photon, they have mass, and substantial mass at that. The W boson weighs about 80 times as much as a proton. The Z boson weighs about 91 times as much. Their large masses are why the weak force has such short range. Heavier force carriers create shorter range forces. The W and Z bosons were predicted by the electroweak theory of Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1960s and 1970s, and discovered at CERN in 1983. Their discovery confirmed the unification of electromagnetism and the weak force and earned multiple Nobel Prizes. The gluons carry the strong nuclear force. There are 8 types of gluons, corresponding to the 8 generators of the symmetry group that describes the strong force. Gluons are massless, like photons, but unlike photons, they carry the charge they mediate. Photons are electrically neutral, but gluons carry color charge, the property that quarks possess and that the strong force acts upon. Because gluons carry color charge, they can interact with each other, not just with quarks. This self-interaction is responsible for the strange properties of the strong force, including confinement and the fact that the force grows stronger with distance rather than weaker. The Higgs boson stands apart from the other bosons. It does not carry a force. Instead, it is the quantum of the Higgs field, the field that gives other particles their masses. The Higgs boson was predicted in 1964 by Peter Higgs and independently by several other physicists. It was finally discovered at the Large Hadron Collider in 2012, nearly 50 years after it was proposed. The discovery was announced on July 4, 2012, and was immediately recognized as one of the most important findings in the history of physics. Peter Higgs and François Englert shared the Nobel Prize in Physics the following year. As the universe expanded and cooled, something remarkable happened. Or rather, something remarkable failed to happen, and we do not understand why. The Big Bang should have created exactly equal amounts of matter and antimatter. For every quark, there should have been an antiquark. For every electron, a positron. For every particle of matter, a corresponding particle of antimatter. This is what the symmetry of our equations predicts. Matter and antimatter are mirror images of each other. They should have been produced in perfect balance. When matter and antimatter meet, they annihilate completely. They convert entirely into energy, into photons, leaving nothing behind. If the early universe contained equal amounts of matter and antimatter, they should have annihilated completely. Every particle should have found its antiparticle partner. The entire universe should have been converted into radiation. No matter would remain. No stars would ever form. No planets. No life. No you. But obviously, that did not happen. We exist. Stars exist. Galaxies exist. Matter clearly won over antimatter. Something broke the perfect symmetry. For every billion antimatter particles, there must have been 1,000,000,001 matter particles. The billion pairs annihilated each other, converting into the radiation that still fills the universe today. But that one extra matter particle in every billion survived. Look around you. Everything you see, everything you touch, everything you are, is made from those survivors. The entire visible universe, all the stars and planets and galaxies, consists of the leftovers from the Great Annihilation. Why was there one extra matter particle in every billion? This is called the problem of baryogenesis, and it remains one of the biggest unsolved mysteries in physics. In 1967, the Soviet physicist Andrei Sakharov identified 3 conditions necessary for this asymmetry to develop. First, there must be processes that violate the conservation of baryon number, processes that can create an imbalance between matter and antimatter. Second, there must be violation of certain symmetries called C-symmetry and CP-symmetry, meaning that the laws of physics must treat matter and antimatter slightly differently. Third, these processes must occur out of thermal equilibrium, meaning the universe must be changing rapidly enough that the reverse processes cannot restore the balance. We have found evidence for CP violation in laboratory experiments. Certain particles, called kaons and B-mesons, decay slightly differently than their antiparticles. Matter and antimatter are not perfect mirrors of each other after all. The universe does distinguish between them, at least a little. But the amount of CP violation we have observed is nowhere near enough to explain the matter-antimatter asymmetry. it falls short by many orders of magnitude. There must be additional sources of CP violation that we have not discovered. There must be physics beyond what we currently understand. This is humbling. Your existence depends on a process we cannot explain. Something happened in the first second of the universe that created the matter you are made of, and we do not know what it was. The equations we write down predict a universe of pure radiation, a cosmos without matter, without structure, without life. Something corrected those equations. Something added a term we have not yet found. Your body is evidence of physics we do not understand. At approximately 10 to the negative 12 seconds after the Big Bang, the universe reached a temperature of about 10 to the 15 degrees Kelvin. This is when one of the most important transitions in cosmic history occurred. The electroweak force, which had remained unified since the end of inflation, finally split into two separate forces. Electromagnetism became distinct from the weak nuclear force. They would never reunite again. At least, not until humans built particle accelerators powerful enough to briefly restore the primordial conditions. This transition is intimately connected to the Higgs field. Before the electroweak transition, all particles were massless. They all traveled at the speed of light, because having no mass means nothing can slow you down. The Higgs field existed, but was in a symmetric state, a high-energy configuration that did not interact with other particles in the way it does now. As the universe cooled below the electroweak transition temperature, the Higgs field underwent what physicists call spontaneous symmetry breaking. It fell into a lower energy state, like water vapor condensing into liquid. In this new state, the Higgs field interacts with certain particles, and this interaction gives those particles mass. Imagine trying to walk through a crowded room. If the room is empty, you can walk freely at your maximum speed. But if the room is filled with people who grab at you and slow you down, your effective speed decreases. The Higgs field is like a crowd that fills all of space. Particles that interact strongly with the Higgs field are slowed down a lot and appear to have large mass. Particles that interact weakly are slowed down less and have small mass. Photons do not interact with the Higgs field at all, so they remain massless and continue to travel at the speed of light. The Large Hadron Collider deserves special mention. It is the largest and most powerful particle accelerator ever built. A circular tunnel 27 kilometers in circumference buried beneath the border between Switzerland and France. Inside the tunnel, two beams of protons travel in opposite directions at 99.999991% of the speed of light. When these beams collide, the energy of their motion converts into mass, creating showers of particles that sophisticated detectors analyze. The LHC recreates conditions that existed in the universe less than a trillionth of a second after the Big Bang. It is a time machine of sorts, allowing us to study the physics of the very early universe in a laboratory on Earth. The discovery of the Higgs boson was the culmination of decades of effort by thousands of scientists and engineers. The LHC itself cost about $10 billion to build. The detectors that identified the Higgs, called ATLAS and CMS, are among the most complex machines ever constructed. Each one contains millions of sensors, sophisticated magnets, and vast computing systems to process the data. The collaboration that discovered the Higgs included more than 6,000 scientists from dozens of countries. It was a triumph of international cooperation and sustained intellectual effort. At approximately 10 to the negative 6 seconds, 1 microsecond after the Big Bang, the universe reached another critical threshold. The temperature had dropped to about 10 trillion degrees Kelvin, roughly 1,000,000 times hotter than the center of the sun, but cool enough for a dramatic transformation to occur. The quark-gluon plasma finally condensed. Quarks, which had been roaming freely, became permanently confined inside composite particles. This transition is called hadronization, and it produced the protons and neutrons that would eventually form the nuclei of atoms. The strong nuclear force, which had been somewhat passive in the quark-gluon plasma, now asserted its dominance. Gluons bound quarks together into tight packages. 3 quarks combined to form each proton and each neutron. 2 up quarks and a down quark made a proton with its positive electric charge. 2 down quarks and an up quark made a neutron with no electric charge. Other combinations formed briefly but quickly decayed into the stable configurations. Along with protons and neutrons, the universe also produced antiprotons and antineutrons. These were the antimatter counterparts, made of antiquarks. And now came the great annihilation. Protons met antiprotons and converted to energy. Neutrons met antineutrons and vanished in flashes of gamma rays. Across the universe, matter and antimatter destroyed each other in an orgy of mutual annihilation. When the annihilation was complete, only that tiny excess of matter remained. One particle in a billion survived. The energy released by all those annihilations added to the radiation bath that filled space. The universe was now 1 microsecond old. It contained protons, neutrons, electrons, photons, and neutrinos. The exotic particles of the earlier epochs had either decayed or annihilated. The fundamental forces had separated into their present forms. The stage was set for the next act in cosmic evolution. At 1 second after the Big Bang, the temperature had dropped to about 10 billion degrees Kelvin. This is still incredibly hot by any earthly standard, about 1,000 times hotter than the center of the sun. But it was cool enough for another important transition. Neutrinos, the ghost particles that barely interact with anything, decoupled from the rest of the universe. Neutrinos are strange particles. They have almost no mass. They interact only through the weak nuclear force and gravity. They can pass through light years of solid lead without hitting anything. Every second, about 100 billion neutrinos from the sun pass through every square centimeter of your body. You never notice because they interact so weakly. But in the early universe, when matter was extremely dense and temperatures were extreme, even neutrinos collided frequently. They were in thermal equilibrium with everything else, constantly exchanging energy with protons, neutrons, and electrons. At 1 second, the universe had expanded and cooled enough that neutrinos stopped colliding. They decoupled from the cosmic plasma and began streaming freely through space. These relic neutrinos are still out there. They fill the entire universe, a cosmic neutrino background analogous to the cosmic microwave background. But because they interact so weakly, we have never directly detected them. Their temperature today is even lower than the microwave background, about 1.95 Kelvin, because they decoupled earlier and have been cooling independently ever since. The first second had seen an astonishing amount of activity. The universe had transitioned from a quark-gluon plasma to a soup of protons and neutrons. The electroweak force had split into electromagnetism, and the weak force, the Higgs field, had given particles their masses. Matter and antimatter had mostly annihilated, leaving only a tiny residue of matter behind. Neutrinos had decoupled and begun their lonely journey through space. All of this happened before the universe was even 1 second old. But protons and neutrons were not yet atomic nuclei. Electrons were not yet bound to anything. The universe was still a plasma, a hot, ionized gas where electrons roamed freely among positively charged nuclear particles. The photons that filled space could not travel far. They constantly scattered off free electrons, bouncing randomly through the cosmic plasma like light in dense fog. The universe was opaque, glowing brilliantly, but impenetrable to any observer who might have existed. As the first second ended, the ratio of protons to neutrons was about 7:1. This ratio would prove crucial for everything that followed. Protons are slightly lighter than neutrons, and in the conditions of the early universe, various processes converted particles back and forth between these two states. As the universe cooled and these processes slowed down, the ratio froze in at 7 protons for every neutron. This ratio would determine how much helium formed during the next phase of cosmic evolution. It would set the chemical composition of the entire universe. The universe had now completed its particle physics phase. The fundamental forces had assumed their present forms. The basic particles that would constitute all matter had been created. The stage was set for nuclear physics to take over. In the next few minutes, the first atomic nuclei would form. The universe would become a cosmic fusion reactor, forging helium from hydrogen in a burst of nucleosynthesis that would last only a few minutes but would determine the chemical composition of the cosmos for all time. The universe was now a few seconds old, and it faced a deadline. Free neutrons are unstable. Left to themselves, they decay. A neutron sitting alone in space will spontaneously transform into a proton, emitting an electron and an antineutrino in the process. The half-life of this decay is about 10 minutes. Half of any collection of free neutrons will be gone in 10 minutes. Half of what remains will be gone in another 10 minutes, and so on. If the universe took too long to form atomic nuclei, all the neutrons would decay into protons. Without neutrons, you cannot build anything heavier than hydrogen. No helium, no lithium, no pathway to the heavier elements that stars would later forge. The universe had a narrow window of opportunity, and that window was closing. The temperature at 10 seconds after the Big Bang was approximately 3 billion degrees Kelvin. This is about 200 times hotter than the core of the Sun. Protons and neutrons were slamming into each other constantly, but every time they tried to stick together, a high-energy photon would blast them apart. The radiation that filled space was too intense. It shattered any nucleus that tried to form. The universe was like a construction site where workers keep trying to build walls, but a demolition crew keeps knocking them down before each wall can be completed. But the universe was cooling. Every moment that passed, the temperature dropped. The photons lost energy. The demolition crew grew weaker. At some point, the builders would be able to work faster than the destroyers could tear down. That moment arrived at approximately 100 seconds after the Big Bang, when the temperature dropped below 1 billion degrees Kelvin. The first step in building heavier nuclei is the simplest possible fusion reaction. 1 proton plus 1 neutron equals deuterium. Deuterium is heavy hydrogen, an isotope with 1 proton and 1 neutron in its nucleus instead of just a single proton. This reaction had been trying to happen since the first second, but the resulting deuterium nuclei kept getting blasted apart by photons. Physicists call this the deuterium bottleneck. Until the universe cooled enough for deuterium to survive, nothing heavier could form. Deuterium is the gateway. Every heavier nucleus must pass through it. At 100 seconds, the bottleneck finally broke. Deuterium began to accumulate. Once deuterium existed in significant quantities, the rest happened quickly. Deuterium plus a proton makes helium-3, an isotope of helium with 2 protons and 1 neutron. Deuterium plus a neutron makes tritium, an isotope of hydrogen with 1 proton and 2 neutrons. Helium-3 plus a neutron makes helium-4, the stable common form of helium with 2 protons and 2 neutrons. Tritium plus a proton also makes helium-4. Multiple pathways led to the same destination. The universe was racing to lock neutrons inside stable nuclei before they could decay. Helium-4 is remarkably stable. Once formed, it does not easily break apart. It became the repository for almost all the neutrons in the universe. The fusion reactions proceeded rapidly, converting available neutrons into helium as fast as the nuclear physics allowed. By the time the universe was about 3 minutes old, the process was essentially complete. The window had closed, the universe had cooled below the temperatures required for fusion. The cosmic reactor shut down. The results of this 3-minute burst of nuclear fusion determined the chemical composition of the universe for all time. Approximately 75% of the mass ended up as hydrogen, simple protons that never found a neutron partner. Approximately 25% ended up as helium-4, the stable product of primordial fusion. Trace amounts of other light elements were produced as well. Deuterium that did not get incorporated into helium survived in small quantities, about 1 atom of deuterium for every 100,000 atoms of hydrogen. Helium-3 remained in even smaller amounts. A tiny bit of lithium-7 was produced through more complex reaction chains. And that was it. No carbon, no oxygen, no nitrogen, no iron, no silicon, none of the elements that make up the Earth, none of the elements that make up your body. The Big Bang produced only hydrogen, helium, and traces of lithium. Everything else, every atom of carbon in your DNA, Every atom of oxygen in the air you breathe, every atom of calcium in your bones, every atom of iron in your blood, all of it was made later, billions of years later, in the cores of stars. This is one of the most important facts about the universe. The Big Bang made the raw material, but it did not make the periodic table. Stars made the periodic table. The carbon in your body was forged in a star that lived and died before our sun was born. The oxygen you are breathing was fused from helium in a stellar core and then scattered into space by a supernova explosion. You are not just a product of the Big Bang. You are a product of generations of stars that processed primordial hydrogen and helium into heavier elements over billions of years. The Big Bang made the universe possible. Stars made you possible. Why did nucleosynthesis stop at lithium? Why did the early universe not continue fusing heavier and heavier elements the way stars do? The answer lies in a quirk of nuclear physics. There are no stable nuclei with 5 nucleons or 8 nucleons. Nucleons are the collective term for protons and neutrons. Helium-4 has 4 nucleons. If you try to add one more nucleon to make a nucleus with 5, the result is unstable. It falls apart almost immediately. If you try to combine 2 helium-4 nuclei to make a nucleus with 8, that is also unstable. It falls apart in a tiny fraction of a second. These gaps at mass 5 and mass 8 create a barrier that primordial nucleosynthesis could not cross. Stars overcome this barrier through a process called the triple alpha reaction. 3 helium-4 nuclei, each also called an alpha particle, collide almost simultaneously to form carbon-12. This bypasses the unstable intermediates, but the triple alpha process requires high densities sustained over millions of years. The early universe was hot, but it was not dense enough for long enough. The expansion diluted the material too quickly. By the time the universe was 20 minutes old, nucleosynthesis was over. The density had dropped too low for fusion to continue. The chemical composition was locked in. The predictions of Big Bang nucleosynthesis are remarkably precise. Given one input parameter, the ratio of baryons to photons in the early universe, physicists can calculate exactly how much hydrogen, helium, deuterium, and lithium should have been produced. These calculations were first performed seriously in the 1960s and 1970s. Observations have been accumulating ever since, and the match is extraordinary. The predicted abundance of helium-4 is about 25% by mass. Observations of the oldest, most pristine regions of the universe show approximately 24 to 25% helium. The predicted abundance of deuterium depends sensitively on the baryon-to-photon ratio, but for the ratio we measure from other observations, the prediction matches the observed deuterium abundance in distant gas clouds to remarkable precision. Helium-3 abundances are harder to measure, but appear consistent with predictions. This agreement between prediction and observation is one of the strongest pieces of evidence that the Big Bang actually happened. There is one discrepancy. The observed abundance of lithium-7 is about 3 times lower than predicted. This is called the cosmological lithium problem, and it has puzzled physicists for decades. The discrepancy is not large enough to overthrow the entire theory, but it is persistent and unexplained. Perhaps some process in stars destroys lithium that would otherwise be observable. Perhaps our nuclear physics calculations have subtle errors. Perhaps there is unknown physics in the early universe that affected lithium production. The lithium problem remains an active area of research, a small cloud on an otherwise clear horizon. The universe at 20 minutes was a very different place than the universe at 1 second. The fundamental forces had separated. The particles had condensed and annihilated, and now the nuclei had formed. But the universe was still a plasma. Electrons remained free, not bound to nuclei. The temperature was still about 100 million degrees Kelvin, far too hot for atoms to form. Photons still scattered constantly off free electrons. The universe remained opaque, a brilliant fog of radiation and matter thoroughly mixed together. This state would persist for a long time, not seconds or minutes, but hundreds of thousands of years. The universe would continue to expand and cool, the plasma gradually thinning, the photons gradually losing energy. Nothing dramatic would happen during this period. No new particles would form. No new elements would be created. The universe was simply waiting, cooling, expanding, drifting toward the next transition. The protons and helium nuclei that filled space were the raw material for everything that would come later. Every star that would ever shine would be made primarily of this primordial hydrogen and helium. Every galaxy that would ever form would inherit this composition. The 75% hydrogen, 25% helium ratio established in the first 3 minutes would be the starting point for all subsequent cosmic chemistry. Stars would process this material, fusing hydrogen into helium, helium into carbon, carbon into oxygen, and so on, up the periodic table. But they would always start with what the Big Bang provided. The nuclei produced in the first 3 minutes still exist today. Not the same individual nuclei, of course. Most primordial nuclei have been processed through stars at least once, but the overall abundances remain a fossil record of those first few minutes. When astronomers measure the helium content of the oldest stars, they are reading a message from the first 3 minutes after the Big Bang. When they measure deuterium in distant gas clouds that have never been inside a star, they are seeing atoms that have remained unchanged for 13.8 billion years. These are among the oldest objects in the universe. Hydrogen nuclei that formed when the cosmos was 3 minutes old and have been drifting through space ever since. The hydrogen in your body is even older than the helium. Some of the hydrogen atoms in the water molecules of your cells are primordial. They are not products of stellar fusion. They are protons that emerged from the quark-gluon plasma at 1 microsecond after the Big Bang and never found a neutron partner during nucleosynthesis. They have persisted through the entire history of the universe, eventually becoming part of gas clouds, then part of the solar nebula, then part of the Earth, then part of the water you drank, then part of you. Those hydrogen atoms are 13.8 billion years old. They are as old as time itself, and they are inside you right now, participating in the chemistry that keeps you alive. The 3-minute miracle was complete. The universe had forged its initial supply of elements. The periodic table had its first entries. Hydrogen and helium would reign supreme for hundreds of millions of years, until the first stars ignited and began the slow process of cosmic enrichment. But that is a story for later. For now, the universe drifted on, a cooling plasma of nuclei and electrons, waiting for the next great transformation. The universe settled into a long quiet period after nucleosynthesis ended. For nearly 400,000 years, nothing dramatic happened. The cosmos simply expanded and cooled. The plasma gradually thinning, the temperature slowly dropping. Nuclei and electrons filled space in roughly equal numbers, mixed with a sea of photons that vastly outnumbered them both. For every proton or helium nucleus, there were about 1 billion photons. Light dominated matter by sheer quantity, though matter would eventually have the last word through gravity. This plasma was opaque. Photons could not travel in straight lines. Every time a photon tried to move through space, it quickly encountered a free electron and scattered off in a random direction. Then, it scattered again and again. The universe was like a dense fog illuminated from within. Light existed everywhere, but it could not propagate. An observer inside this plasma, had one existed, would have seen only a brilliant white glow in every direction. No structure would be visible. No distance could be perceived. Just light, everywhere, going nowhere. The mean free path of a photon, the average distance it could travel before scattering, was remarkably short. Despite the universe being enormous by this point, spanning millions of light years, photons were trapped in an endless random walk. They bounced from electron to electron like pinballs, their paths chaotic and unpredictable. Information could not travel through this medium at the speed of light. It traveled at the speed of the random walk, which was far slower, but the temperature was falling. At 400,000 years after the Big Bang, it had dropped to approximately 3,000 degrees Kelvin. This is about half the temperature of the surface of the Sun. Still hot by everyday standards, but cool by cosmological ones. At this temperature, something extraordinary happened. Electrons began to combine with nuclei to form neutral atoms, Protons captured electrons to become hydrogen atoms. Helium nuclei captured 2 electrons each to become helium atoms. The plasma converted into a gas. This process is called recombination, though the name is misleading. It was not recombination at all. The electrons and nuclei had never been combined before. This was the first time atoms had ever existed in the universe. But the term recombination comes from laboratory physics, where this same process happens when plasmas cool down. Electrons recombine with ions to form neutral atoms. The name stuck even though it does not quite fit the cosmological context. Recombination changed everything. Neutral atoms do not scatter photons the way free electrons do. A photon can pass right through a hydrogen atom without interacting, as long as the photon's energy does not match one of the atom's specific absorption frequencies. The universe transformed from opaque to transparent almost suddenly. The fog lifted. Light broke free. The photons that had been trapped in the plasma, bouncing endlessly from electron to electron, were suddenly released. They began streaming across the universe in straight lines. They have been traveling ever since. Those same photons, released 380,000 years after the Big Bang, are still traveling through space today. When they happen to arrive at Earth and enter our telescopes, we detect them as the cosmic microwave background radiation. The cosmic microwave background is the oldest light in the universe. It is a snapshot of the cosmos at 380,000 years old, the moment when the universe first became transparent. Nothing we observe directly can be older than this. Before recombination, the universe was opaque. Any light from earlier times has been scattered and thermalized beyond recognition. The cosmic microwave background is our earliest possible photograph of the universe. A baby picture taken when the cosmos was only about 0.003% of its current age. When this light was released, it was not microwave radiation. It was visible light, yellowish-orange in color, with a temperature of about 3,000 degrees Kelvin. That is roughly the color of an incandescent light bulb, perhaps slightly redder. The entire universe glowed at this color. The sky was brilliantly luminous in every direction, filled with the light of the cooling plasma. But the universe has expanded enormously since then. Space has stretched by a factor of about 1,100. And when space stretches, the light traveling through it stretches too. Wavelengths increase. The yellowish-orange light of recombination has been stretched into the microwave part of the spectrum. What was once visible light is now invisible to human eyes. The temperature has dropped from 3,000 degrees to just 2.725 degrees Kelvin, about 270 degrees below 0 Celsius. The cosmic microwave background is now a faint cold glow filling all of space, detectable only with sensitive radio telescopes. The discovery of the cosmic microwave background is one of the great stories of 20th century science. In 1965, 2 radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for satellite communication experiments. They encountered a persistent noise that they could not eliminate. It came from every direction in the sky. It did not vary with time of day or season of the year. They checked their equipment obsessively. They even cleaned pigeon droppings from inside the antenna, wondering if bird waste might be causing the signal. Nothing helped. The noise persisted. Meanwhile, just 30 miles away at Princeton University, a group of physicists, led by Robert Dicke, was building an instrument specifically to search for the cosmic microwave background. They knew that if the Big Bang theory was correct, this radiation should exist. They were racing to detect it before anyone else. When Penzias and Wilson learned about the Princeton group's work, they realized what they had found. The persistent noise was not equipment malfunction. It was the afterglow of the Big Bang itself. They had accidentally discovered the cosmic microwave background while trying to do something else entirely. They shared the Nobel Prize in Physics in 1978 for this discovery, a discovery they had not even been looking for. The cosmic microwave background was the evidence that finally convinced most scientists that the Big Bang theory was correct. Before this discovery, there were competing theories of cosmology. The steady-state theory proposed that the universe had no beginning. that it had always existed in roughly its present form, with new matter continuously created to fill the gaps as the universe expanded. This theory was elegant and appealing to many physicists, but it could not explain the cosmic microwave background. If the universe had no beginning, if it had not started in a hot, dense state, there was no reason for this radiation to exist. The steady-state theory died when the cosmic microwave background was discovered. The Big Bang won. But the cosmic microwave background is not perfectly uniform. It has tiny variations in temperature from one direction to another. These variations are incredibly small, only about 1 part in 100,000. If you represented the average temperature as a wall painted a uniform shade of gray, the variations would be like applying a second coat of paint that differed from the first by less than a millimeter in thickness. You would not be able to see the difference with your eyes, but sensitive instruments can detect it. These tiny variations are the most important feature of the cosmic microwave background. They are the seeds of all structure in the universe. The hot spots correspond to regions that were slightly denser than average at the time of recombination. The cold spots correspond to regions that were slightly less dense. Over the following billions of years, gravity amplified these tiny differences. Denser regions attracted more matter and became denser still. Less dense regions lost matter to their neighbors and became emptier. The hot spots became galaxy clusters. The cold spots became cosmic voids. The pattern of temperature variations in the cosmic microwave background is a map of where galaxies would eventually form. 3 major space missions have mapped the cosmic microwave background with increasing precision. The Cosmic Background Explorer, or COBE, launched in 1989, made the first detection of the temperature variations. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped the full sky with much higher resolution. The Planck satellite, launched in 2009 by the European Space Agency, produced the most detailed maps yet, measuring temperature variations down to scales of about 5 arc-minutes, 1/6 the diameter of the full moon. COBE carried 3 instruments designed to study the microwave background with unprecedented precision. The Far Infrared Absolute Spectrophotometer, or FIRAS, measured the spectrum of the radiation and found that it matched a perfect blackbody to better than 1 part in 10,000. This was the most perfect blackbody spectrum ever measured, far more precise than any laboratory source. It confirmed that the universe had indeed passed through a hot, dense, thermal equilibrium state, exactly as the Big Bang predicted. COBE's other major instrument, the Differential Microwave Radiometer, or DMR, searched for variations in the temperature of the radiation across the sky. In 1992, the COBE team announced the detection of temperature variations at the level of about 1 part in 100,000. George Smoot, who led the DMR team, described the discovery as like seeing the face of God. He and John Mather, who led the FIRAS team, shared the Nobel Prize in Physics in 2006. WMAP's data allowed cosmologists to measure the fundamental parameters of the universe with percent-level precision. The age of the universe, the curvature of space, the density of ordinary matter, dark matter, and dark energy, the amplitude and spectrum of the primordial fluctuations. Before WMAP, cosmology was sometimes called the science of a few percent uncertainties. After WMAP, it became precision cosmology. The parameters were nailed down. The Big Bang model was confirmed in extraordinary detail. The Planck satellite pushed precision even further. Planck mapped the microwave background at 9 different frequencies with angular resolution about 3 times better than WMAP. The Planck maps are the most detailed images we have of the early universe, containing millions of pixels of information about conditions 380,000 years after the Big Bang. Planck's results confirmed the standard cosmological model, but also revealed some tantalizing anomalies. There appear to be patterns in the data that are not predicted by the simplest versions of inflation. Large-scale asymmetries, alignments that seem improbable, a cold spot that is larger than expected. These anomalies are not significant enough to overthrow the standard model, but they hint at physics we might not understand. The microwave background contains more information than just temperature variations. It is also polarized. Light can vibrate in different directions perpendicular to its motion, and the cosmic microwave background has a slight preference for certain directions of vibration. This polarization arises from the scattering of radiation off electrons just before recombination. The pattern of polarization encodes additional information about the early universe, including potential signatures of gravitational waves from inflation. Gravitational waves are ripples in space-time, predicted by general relativity and directly detected for the first time in 2015 by the LIGO Observatory. But the gravitational waves from inflation would be primordial, generated in the first fraction of a second, stretched by inflation to cosmic scales. They would have left a distinctive signature in the polarization of the microwave background, a pattern called B-mode polarization. Detecting this pattern would be powerful evidence for inflation. In 2014, a team using the BICEP 2 telescope at the South Pole announced that they had detected B-mode polarization from primordial gravitational waves. The announcement made headlines around the world. It seemed like the smoking gun for inflation had finally been found. But subsequent analysis revealed that the signal was contaminated by dust in our own galaxy. The BICEP 2 detection was not primordial gravitational waves after all. The search continues, with more sensitive instruments and better understanding of galactic foregrounds. The cosmic microwave background is a wall. We cannot see beyond it with light. Before recombination, the universe was opaque. Any photons from earlier times have been scattered and absorbed and re-emitted so many times that they carry no information about their origins. The cosmic microwave background represents the surface of last scattering, the earliest moment we can directly observe with electromagnetic radiation. Everything we know about earlier times, about nucleosynthesis, about the quark-gluon plasma, about inflation, about the Planck epoch, comes from theory and indirect evidence, not from direct observation. The microwave background is the edge of our visible universe in time, if not in space. But the universe did not end at recombination. It continued to evolve. Neutral atoms now filled space, hydrogen and helium in a cooling gas. The photons of the cosmic microwave background streamed freely, no longer interacting with matter. And gravity, patient gravity, began its long, slow work of gathering matter into structures. The tiny density variations that showed up as temperature variations in the microwave background would gradually grow. Over millions of years, they would become pronounced enough to collapse under their own gravity. The first stars would ignite, the first galaxies would form. The cosmic dark ages would give way to the cosmic dawn. The universe had gone dark. Not metaphorically dark, not poetically dark, but literally, physically dark. For the first time since the Big Bang, there was no light being produced anywhere in the cosmos. The cosmic microwave background had shifted out of the visible spectrum, its photons stretched by expansion into infrared and then into microwaves, invisible to any eye that might have existed. No stars had formed yet. No galaxies glowed in the void. The universe was filled with neutral hydrogen and helium gas, cold and dark and utterly silent, drifting through an expanding emptiness that would persist for hundreds of millions of years. This era is called the Cosmic Dark Ages, and the name is perfectly apartment of fundamentarpent. Imagine a darkness more complete than anything you have ever experienced. On Earth, even on the darkest night, there is always some light. Starlight filters through the atmosphere. The moon reflects sunlight. City glow pollutes the horizon. In space, stars blaze against the black. But during the cosmic dark ages, there were no stars. There was no reflected light. There was only the fading afterglow of the Big Bang, stretched beyond visibility, and the cold gas that filled the universe, emitting nothing, absorbing nothing, simply existing in the dark. The temperature during this era dropped steadily as the universe expanded. At recombination, it had been about 3,000 degrees Kelvin. By the time the Dark Ages ended, it had fallen to only about 60 degrees Kelvin. Still cold enough to freeze any substance we know, but warm compared to the 2.7 Kelvin temperature of the universe today. The gas that filled space was cooling along with the radiation, losing energy to the expansion, becoming ever more diffuse as the cosmos stretched. But the Dark Ages were not empty of activity. Gravity was at work. The tiny density variations imprinted during inflation and visible in the cosmic microwave background were being amplified. Regions slightly denser than average were pulling in matter from their surroundings. Dark matter, which does not interact with light and therefore was not affected by the pressure of radiation before recombination, had already begun clumping together. Dark matter halos were forming, invisible concentrations of mass scattered throughout the universe, growing steadily larger as gravity drew more matter into them. Dark matter is strange stuff. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should, based on their visible mass. Galaxy clusters bend light more strongly than their visible matter can explain. The cosmic microwave background has patterns that require dark matter to form. But we do not know what dark matter actually is. It does not emit light. It does not absorb light. It passes through ordinary matter like a ghost. Despite decades of searching, no experiment has ever directly detected a dark matter particle. It remains one of the great mysteries of modern physics, a substance that makes up about 27% of the universe and yet has never been identified. During the cosmic dark ages, dark matter was the architect of structure. Because it does not interact with light, dark matter was not held up by radiation pressure the way ordinary matter was before recombination. It could begin collapsing under gravity much earlier. By the time ordinary matter was released at recombination, dark matter had already formed a network of halos and filaments, a cosmic scaffolding onto which ordinary matter would fall. The gas that filled the universe after recombination drifted toward these dark matter concentrations, pulled by gravity, accumulating in the invisible wells that dark matter had already dug. The cosmic web that we see today, the vast network of galaxy filaments and clusters and voids that spans the observable universe, was being laid down during the Dark Ages. Dark matter formed the skeleton. Ordinary matter followed along, tracing the paths that dark matter had carved. The distribution of galaxies that we observe today reflects the distribution of dark matter that emerged during this era. Every galaxy sits inside a dark matter halo. Every galaxy cluster is embedded in a larger dark matter structure. The visible universe is a decoration on an invisible framework. Light strung on a dark tree. For perhaps 200 million years, this process continued in darkness. Gas accumulated in dark matter halos. The densest regions grew denser still. Pressure built up as gas compressed under its own gravity. Temperature rose in the cores of the densest clumps, heated by gravitational contraction, but there was still no light. The gas was not hot enough to glow visibly. The universe remained dark, patient, waiting. The first light came from the first stars. These were not stars like our sun. They were monsters, giants beyond anything that exists in the universe today. The first generation of stars, called Population 3 stars by astronomers, formed from pristine gas that had never been inside a star before. This gas contained only hydrogen and helium, the products of Big Bang nucleosynthesis. It contained no carbon, no oxygen, no iron, none of the heavier elements that astronomers call metals. This lack of metals had profound consequences for how the first stars formed and what they looked like. In the present-day universe, gas clouds cool efficiently because they contain heavy elements. Carbon and oxygen atoms radiate energy away, allowing gas to lose heat and contract. This efficient cooling allows gas to fragment into small pieces, producing stars of modest mass like our sun. But primordial gas lacked these cooling agents. It could only cool through molecular hydrogen, a much less efficient process. Without efficient cooling, gas clouds could not fragment into small pieces. They collapsed as single massive units. The first stars were enormous, perhaps 100 to 1,000 times the mass of our sun. They were blue-white and blindingly luminous, shining with the light of millions of suns. These first stars ignited approximately 200 to 400 million years after the Big Bang. The exact timing remains uncertain, because we have not directly observed population 3 stars. They are too far away, too faint individually, and they lived too briefly to have survived to the present day. We infer their properties from theory and from indirect observations of their effects on the universe around them. The first stars burned fast and died young. Massive stars consume their nuclear fuel at prodigious rates. A star 100 times the mass of the Sun might exhaust its hydrogen in only a few million years, compared to the 10 billion-year lifetime of a star like ours. The first stars lived for perhaps 2 to 3 million years, a cosmic eye blink, before meeting violent ends. When the first stars died, they died dramatically. Stars above a certain mass threshold explode as supernovae, blasting their outer layers into space at thousands of kilometers per second. The most massive stars may have collapsed directly into black holes, swallowing much of their mass but still expelling enormous amounts of energy. These explosions had two crucial effects on the universe. First, they scattered heavy elements into space. The cores of massive stars are nuclear furnaces where hydrogen fuses into helium, helium into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron. These elements, created for the first time in the universe, were blasted outward by the supernova explosions. They mixed with the surrounding primordial gas, polluting it with metals. The next generation of stars would form from this enriched gas. They would be smaller, cooler, longer-lived. The chemical evolution of the universe had begun. Second, the radiation from the first stars began to transform the universe around them. Massive hot stars emit enormous amounts of ultraviolet light. This high-energy radiation ionizes hydrogen atoms, stripping away their electrons and converting neutral gas back into plasma. Around each first star, a bubble of ionized hydrogen formed, a sphere of plasma embedded in the surrounding neutral gas. These bubbles were called HI regions, and they were the first pockets of ionized gas in a universe that had been neutral since recombination. As more and more first stars formed, these ionized bubbles grew and multiplied. They overlapped. They merged. Gradually, the universe transformed from mostly neutral to mostly ionized. This process is called reionization, and it marks the end of the cosmic dark ages. The universe that had become neutral at recombination was being ionized again, this time by starlight rather than by the primordial heat of the Big Bang. Reionization was not instantaneous. It took hundreds of millions of years to complete. The earliest stars created the first ionized bubbles. Later generations of stars, along with the first quasars, powered supermassive black holes consuming matter at the centers of young galaxies, continued the process. By about 1 billion years after the Big Bang, reionization was largely complete. The intergalactic medium was ionized, and it has remained ionized ever since. The neutral gas of the Dark Ages was transformed into the hot, thin plasma that fills the space between galaxies today. The James Webb Space Telescope has revolutionized our view of the early universe. Launched on Christmas Day 2021 and beginning science operations in 2022, Webb is the most powerful space telescope ever built. Its primary mirror, 6.5 meters across and made of 18 hexagonal segments coated in gold, collects infrared light from the most distant objects in the cosmos. Its position at the second Lagrange point, about 1.5 million kilometers from Earth, keeps it cold and stable, far from the thermal contamination of our planet. Webb was designed specifically to see the first galaxies. The expansion of the universe stretches light from distant objects to longer wavelengths. A galaxy that emitted ultraviolet light when the universe was young appears to us in infrared. The more distant the galaxy, the more extreme the stretching, the deeper into the infrared we must look. Webb's instruments are optimized for exactly these wavelengths, allowing it to detect galaxies that were invisible to previous telescopes. In its first deep field images, released in July 2022, Webb revealed thousands of galaxies in a patch of sky, smaller than a grain of sand, held at arm's length. Some of these galaxies emitted their light when the universe was less than 1 billion years old. They appeared as tiny red smudges, their light stretched by cosmic expansion, their details blurred by vast distance. But even these blurry smudges contained information. Their brightness indicated how many stars they contained. Their colors revealed their stellar populations. Their shapes suggested their dynamical states. What Webb found was surprising. Some of these early galaxies are more massive and more luminous than our models predicted. According to standard theories of galaxy formation, there should not have been enough time in the young universe for such substantial galaxies to assemble. Galaxies grow through mergers, through the gradual accumulation of smaller systems into larger ones. This takes time. A galaxy with billions of stars should not exist when the universe was only a few 100 million years old. And yet there they are, plainly visible in Webb's images. Webb has also discovered galaxies at record-breaking distances. As of 2024, the most distant confirmed galaxy, with the designation JADE GS-Z140, emitted its light when the universe was only about 290 million years old. This galaxy existed before most of the stars in the universe had formed, before the epoch of reionization was complete, in an era when the cosmos was still largely dark. Yet this galaxy is surprisingly bright, suggesting vigorous star formation in an extremely young universe. The light from JADE GS-V140 has been traveling for over 13.5 billion years to reach us. When that light began its journey, the Milky Way did not exist. The Sun did not exist. The solar system would not form for another 9 billion years. The light was ancient before Earth was born, and yet it arrived at Webb's detectors in 2023, carrying information about a time we can barely imagine, a time when the universe was less than 3% of its current age. The first black holes are another mystery. Supermassive black holes, containing millions or billions of solar masses, sit at the centers of most large galaxies today. They grew from smaller seeds, but what were those seeds? One possibility is that they grew from the remnants of the first stars. Population 3 stars that were massive enough might have collapsed directly into black holes of tens or hundreds of solar masses. These black holes could then have grown by accreting gas and merging with each other. But this growth takes time, and we see supermassive black holes in quasars less than 1 billion years after the Big Bang. It is not clear whether there was enough time for them to grow from stellar mass seeds. An alternative hypothesis is that the first black holes formed directly from collapsing gas clouds without passing through a stellar phase. Under the right conditions, a massive gas cloud could collapse directly into a black hole of tens of thousands of solar masses. These direct collapse black holes would have a head start on growth, potentially explaining the early quasars. But the conditions required for direct collapse are restrictive, and it is not clear how common such events could have been. The transition from the Dark Ages to the era of galaxies and stars is the transition from a simple universe to a complex one. Before the first stars, the universe was almost featureless. Hydrogen and helium gas, dark matter halos, and nothing else. After the first stars, complexity exploded. Heavy elements enabled new chemistry. Rocky planets became possible. The foundations for life were laid. Everything interesting in the universe, everything structured and intricate and beautiful, traces back to those first lights igniting in the darkness of the cosmic dawn. We have traveled far through the history of the universe, from the Planck epoch to the cosmic dawn, from temperatures beyond imagination to the cold darkness between galaxies. But how do we know any of this actually happened? How can we be confident that events 13.8 billion years ago unfolded as we have described? The answer lies in evidence. Multiple independent lines of evidence that all point to the same conclusion. The Big Bang is not a guess. It is not a creation myth dressed in scientific language. It is a theory supported by observations so compelling that virtually every working cosmologist accepts it as the foundation of our understanding. The first pillar of evidence is the expansion of the universe. In 1929, Edwin Hubble published observations showing that distant galaxies are moving away from us. The farther away a galaxy is, the faster it recedes. This relationship, now called Hubble's law, is exactly what you would expect if space itself is expanding. Galaxies are not flying through space away from a central point. Space is stretching, carrying galaxies along with it. Every galaxy sees every other galaxy receding, just as dots on a balloon see each other move apart as the balloon inflates. If the universe is expanding now, it must have been smaller in the past. Run the clock backward far enough, and everything was compressed into an incredibly hot, dense state. The expansion we observe today is the direct continuation of the expansion that began at the Big Bang. This is not speculation, it is geometry. The same equations that describe the expansion predict a beginning, a moment when the scale factor was zero and density was infinite. That singularity may be an artifact of our incomplete physics, but the expansion toward it is undeniable. The second pillar is the cosmic microwave background radiation. We have discussed this at length. The existence of this radiation, its temperature, its spectrum, and its tiny variations all match the predictions of the Big Bang theory with extraordinary precision. No competing theory has ever explained the cosmic microwave background. The steady-state theory, which proposed an eternal universe with no beginning, simply could not account for this pervasive glow. The Big Bang predicted it. The Big Bang was confirmed by it. The third pillar is the abundance of light elements. Big Bang nucleosynthesis predicts that the universe should be about 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium. This is exactly what we observe. The helium abundance in the oldest, most pristine regions of the universe matches the prediction perfectly. The deuterium abundance, which is sensitive to the density of ordinary matter in the early universe, matches as well. There is no other known process that can produce these abundances. Stars make helium from hydrogen, but they cannot make enough to explain the cosmic helium content. The deuterium is even more telling, because stars destroy deuterium rather than create it. All the deuterium in the universe must be primordial, created in the first 3 minutes after the Big Bang. The fourth pillar is the evolution of cosmic structure. When we look at distant galaxies, we are looking back in time. Light from a galaxy 1 billion light-years away shows us that galaxy as it was 1 billion years ago. We can observe the universe at different ages simply by looking at different distances. What we see is exactly what the Big Bang predicts. Distant galaxies are smaller, more irregular, more actively forming stars than nearby galaxies. Galaxy clusters at high redshift are less developed than local clusters. The universe has been evolving, growing more structured and complex over time. A universe that had always existed would not show this evolution. But a universe that began in a hot, dense state and has been cooling and expanding ever since would, and does. These four pillars together make the Big Bang one of the most well-supported theories in all of science. But let us be honest about what we do not know. Let us acknowledge the mysteries that remain, the questions that keep physicists awake at night, the gaps in our understanding that may never be filled. The first great mystery is the singularity itself. General relativity, when applied to the early universe, predicts that the Big Bang began with a singularity, a point of infinite density and infinite temperature, but infinities in physics almost always indicate that our theory has broken down. The singularity is probably not a real physical state. It is a sign that we need a more complete theory, one that combines general relativity with quantum mechanics. We do not have that theory. We do not know what happened at time zero, or whether the concept of time zero even makes sense. The second great mystery is what caused the Big Bang. This might be a meaningless question if time itself began at the Big Bang, but it may have an answer if the Big Bang emerged from some prior state, whether a collapsing previous universe, a quantum fluctuation from some underlying void, or a process in a higher dimensional space that we cannot perceive. We do not know. We may never know. The third great mystery is the matter-antimatter asymmetry. The Big Bang should have produced equal amounts of matter and antimatter. They should have annihilated completely, leaving a universe of pure radiation, but matter won by 1 part in a billion, and we exist because of that victory. We have found CP violation, the slight asymmetry in how physics treats matter and antimatter. but the known sources of CP violation are nowhere near strong enough to explain the observed asymmetry. Something else happened. Some unknown physics that gave matter its edge. Your existence depends on a process we cannot explain. The fourth great mystery is dark matter. We know it exists. We can measure its gravitational effects. We can map its distribution, but we have never detected a dark matter particle directly. We do not know what it is made of. After decades of experiments with increasingly sensitive detectors, we have come up empty. Dark matter interacts gravitationally, but apparently not through any of the other forces we understand. It remains invisible, detectable only by its effects, a ghost that shapes the universe but refuses to reveal itself. The Hubble tension is one of the most discussed problems in contemporary cosmology. It concerns the rate at which the universe is expanding, a number called the Hubble constant. Two different methods of measuring this constant give different answers, and the discrepancy has persisted despite years of effort to resolve it. The first method uses the cosmic microwave background. By analyzing the patterns of hot and cold spots in the CMB, cosmologists can infer the properties of the early universe, including how fast it was expanding. Running their models forward to the present day, they predict what the Hubble constant should be now. The Planck satellite measured this value as approximately 67.4 kilometers per second per megaparsec. The second method uses observations of the nearby universe. Astronomers measure the distances to nearby galaxies using standard candles, objects of known intrinsic brightness. Cepheid variable stars are one such standard candle. Type Ia supernovae are another. This method yields a value of approximately 73 kilometers per second per megaparsec. The discrepancy is about 8%. That might sound small, but both measurements claim uncertainties of only about 1%. The difference is statistically significant, more than 5 standard deviations. Either one of the measurements is wrong, or there is something about the universe that our standard model does not capture. If the measurements are both correct, the implication is profound. Something must have happened between the early universe and the present that our standard model does not account for. Perhaps dark energy is not constant, but has changed over time. Perhaps there is a new particle species that affected the expansion rate. Perhaps our theory of gravity needs modification on cosmological scales. All of these possibilities are being explored. The fifth great mystery is dark energy. The expansion of the universe is not just continuing, it is accelerating. Something is pushing space apart, counteracting gravity on cosmic scales. We call this something dark energy, but the name is a placeholder for our ignorance. Dark energy makes up about 68% of the universe, yet we have no idea what it is. It might be the cosmological constant, an energy inherent to empty space itself. It might be a dynamic field that changes over time. It might be evidence that our theory of gravity is wrong on the largest scales. We do not know. The sixth great mystery is inflation. We have described inflation as the solution to the horizon problem, the flatness problem, and the monopole problem. The cosmic microwave background shows patterns consistent with inflationary predictions. But we have not directly detected the inflation field. We have not observed the primordial gravitational waves that inflation should have produced. Inflation remains a hypothesis, widely accepted but not proven. Some physicists have proposed alternative scenarios that might explain the same observations. The very early universe remains contested territory. The dark matter mystery extends beyond simply not knowing what dark matter is. There are also puzzles about how dark matter behaves. The standard model of dark matter, called cold dark matter, makes specific predictions about the structure of dark matter halos. These predictions match observations on large scales, but have had trouble on smaller scales. One puzzle is the cusp core problem. Cold dark matter simulations predict that dark matter halos should have dense central cusps, regions where the density rises steeply toward the center. But observations of dwarf galaxies suggest that their dark matter distributions have constant density cores instead. The dark matter seems less concentrated in the centers than simulations predict. Another puzzle is the missing satellites problem. Simulations predict that a galaxy like the Milky Way should have thousands of small dark matter halos orbiting it. But we observe only dozens of satellite dwarf galaxies. Where are the rest? One possibility is that they exist but contain no stars, making them invisible. Another possibility is that our simulations are wrong. These mysteries are not failures of the Big Bang Theory. They are its frontiers. Science advances by identifying what it does not know and working to understand it. The Big Bang model is not complete. It has gaps, puzzles, unresolved questions, but its core predictions have been confirmed by observation after observation. The universe began in a hot, dense state about 13.8 billion years ago and has been expanding and cooling ever since. This much we know. The details of how it began, what drove its earliest moments, what most of it is made of, these remain mysteries. Gravitational wave astronomy has opened a new window on the universe. Since the first detection of gravitational waves in 2015, the LIGO and Virgo observatories have detected dozens of events, mostly mergers of black holes and neutron stars. These observations have confirmed predictions of general relativity, revealed black holes in unexpected mass ranges, and provided new ways to measure cosmic distances. In the future, gravitational wave observations might probe the very early universe. Space-based detectors, like the proposed LISA mission, could detect gravitational waves from the epoch of inflation if they exist and are strong enough. Ground-based networks will become more sensitive, detecting more events, building a census of black holes and neutron stars throughout the cosmos. Gravitational waves carry information that electromagnetic radiation cannot provide. They pass through matter unimpeded, reaching us from regions and eras that light cannot escape. The next decades will bring new telescopes, new detectors, new methods. The Vera Rubin Observatory will map the sky repeatedly, discovering millions of transient events and tracing the distribution of dark matter through gravitational lensing. The Square Kilometre Array will observe radio waves from the epoch of radionization, mapping hydrogen gas in the early universe. Future space missions will measure the cosmic microwave background polarization with unprecedented precision. Each new instrument will test our theories and potentially reveal new mysteries, and perhaps they should remain mysteries, at least for now. A universe we fully understood would be smaller than we are. The mysteries keep the cosmos larger than our minds. There is always more to discover, more to wonder about, more to explore. The Big Bang Theory has given us a framework for understanding cosmic history, but it has not closed the book. The book remains open, its pages still being written, its ending still unknown. That is the honest state of our knowledge. We know a great deal. We have learned more in the past century than in all of previous human history. But the universe is vast, and our understanding is still a small light in an enormous darkness. We have journeyed far tonight. We have traveled from the first inconceivable fraction of a second to the ignition of the first stars, from temperatures that make the cores of suns seem frozen to the cold emptiness between galaxies. We have watched forces separate from their primordial unity. Particles condense from pure energy. Nuclei forge in a 3-minute furnace. Atoms form as the universe cooled through its 400,000th year. We have seen light break free to travel across the cosmos, still detectable today as the faint whisper of the cosmic microwave background. We have witnessed the Dark Ages give way to the first dawn, stars igniting in the void, galaxies assembling from the cosmic web. And we have confronted the mysteries that remain, the questions that our equations cannot yet answer, the boundaries of human knowledge that may or may not be permanent. Now it is time to ask a different kind of question. What does any of this mean? Not scientifically, but personally. What does it mean for you, lying here in the darkness, breathing air made of atoms, forged in ancient stars, thinking thoughts carried by electrical signals in a brain built from elements scattered by supernovae? The Big Bang is not just a story about the distant past. It is your story. It is the story of how you came to exist, how anything came to exist, how the universe bootstrapped itself from nothing we can describe into everything we can see. The hydrogen atoms in your body are primordial. Let that sink in for a moment. Some of the hydrogen atoms in the water molecules of your cells have existed since the universe was 3 minutes old. They emerged from the quark-gluon plasma at 1 microsecond after the Big Bang. They survived the Great Annihilation when matter and antimatter destroyed each other. They drifted through the cosmic dark ages, became part of gas clouds that collapsed into the first stars, were expelled by supernova explosions, drifted again through interstellar space, became part of the nebula that formed our solar system, became part of Earth, became part of the water cycle, became part of you. Those atoms are 13.8 billion years old. They have been part of more structures, more processes, more transformations than you can possibly imagine. And right now, they are participating in the chemistry that keeps you alive. The heavier atoms in your body have a different history, but one equally profound. The carbon that forms the backbone of your DNA was forged in the core of a star that lived and died before our sun was born. That star fused hydrogen into helium in its core for millions of years. When the hydrogen ran out, it fused helium into carbon through the triple alpha process, 3 helium nuclei combining in quick succession to form a carbon nucleus. That carbon was expelled when the star died, either blown off in stellar winds or scattered by a supernova explosion. It mixed with interstellar gas, became part of a new cloud, collapsed with that cloud to form our solar system, became part of Earth, became part of the organic molecules from which life arose, became part of the long chain of evolution that led to you. The carbon in your body was nuclear ash from a stellar furnace, recycled into the raw material of life. The cosmic calendar offers another way to appreciate the scale of time we have been discussing. Imagine compressing the entire history of the universe into a single year. The Big Bang occurs at midnight on January 1st. The present moment is midnight on December 31st. Every month represents a bit more than 1 billion years. Every day represents about 40 million years. Every second represents about 440 years. On this calendar, the first stars do not ignite until sometime in January, perhaps around January 10th. The Milky Way galaxy does not form until around March. Our solar system does not coalesce until early September, around September 2nd. Life on Earth appears around September 21st. But for months after that, life remains microscopic. Simple, single-celled organisms dominate the planet through October and November. Multicellular life does not appear until mid-December, around December 14th. The Cambrian explosion, when complex animals first diversified, occurs around December 17th. Dinosaurs appear on December 25th, Christmas Day. They dominate the planet for several days before going extinct on December 30th, around 6 in the morning. Mammals, which had been small and marginal, begin to diversify. Primates appear on December 31st, in the early morning hours. The first hominids, our distant ancestors, appear around 10:30 p.m. on December 31st. Anatomically modern humans do not appear until about 11:52 p.m. on December 31st, 8 minutes before midnight. All of recorded human history, everything since the invention of writing, fits into the last 14 seconds. The time since Columbus reached the Americas is about 1 second. The time since you were born is a tiny fraction of a second, too small to register on this calendar. You exist in the last second of the cosmic year. Everything you have ever known, everyone you have ever met, every event in human history fits into an interval so brief that it barely registers against the vast sweep of cosmic time. This is humbling. It puts all human concerns into perspective. Our wars and triumphs, our art and science, our loves and losses, all of it is a brief flicker in the cosmic darkness, a momentary pattern in the endless churning of matter and energy. And yet that brief flicker is precious. The universe has existed for 13.8 billion years, but for most of that time, there was no one to observe it, no one to wonder about it, no one to trace its history and contemplate its mysteries. The cosmos produced galaxies and stars and planets, but it did not produce awareness until very recently. You are part of that awareness. You are one of the ways the universe has found to know itself. The future of the universe extends far beyond the cosmic calendar. If we scale our calendar forward, The universe will continue to expand and cool for vastly longer than it has already existed. Stars will continue to form for perhaps another trillion years, roughly 100 cosmic years on our calendar. But eventually, the gas supply will be exhausted. Star formation will cease. The last stars will be red dwarfs, dim and long-lived, burning their fuel slowly over tens of trillions of years. After about 100 trillion years, the last red dwarfs will fade. The universe will go dark again, this time permanently. Galaxies will become collections of stellar remnants, white dwarfs cooling toward absolute zero, neutron stars spinning down, black holes slowly evaporating through Hawking radiation. This era, called the degenerate era, will last far longer than the current age of the universe, perhaps 10 circumflex 40 years or more. Eventually, even protons may decay. If grand unified theories are correct, protons are not perfectly stable. They decay with a half-life perhaps 10 circumflex 34 years or longer. After enough time, all ordinary matter will have decayed into radiation and leptons. The universe will consist of electrons, positrons, neutrinos, and photons, all at incredibly low energies, spread incredibly thin across an incredibly vast space. Black holes will be the last complex objects to remain. But even they are not eternal. Stephen Hawking showed in 1974 that black holes radiate energy through a quantum mechanical process now called Hawking radiation. This radiation is incredibly weak for large black holes, but causes them to shrink over time. A black hole with the mass of the Sun would take about 10 circumflex 67 years to evaporate. The supermassive black holes at the centers of galaxies would take far longer, perhaps 10 circumflex 100 years, but eventually, even they would vanish, converting their mass entirely into radiation. After the last black holes evaporate, the universe enters its final state, a condition sometimes called heat death. No more structure remains. No more energy gradients can do work. The universe is in thermodynamic equilibrium, a state of maximum entropy where nothing interesting can ever happen again. This is not death in the sense of decay and destruction. It is death in the sense of absolute stillness, perfect uniformity, eternal changelessness. We live in a special time, early in cosmic history, when the universe is still full of structure and activity. Stars are shining, galaxies are spinning, planets are orbiting. Life has emerged on at least one world and may have emerged on many others. The universe is interesting right now, and it will remain interesting for billions of years to come. But this era is not typical. Most of the universe's future will be dark and empty and still. We are fortunate to exist when we do, in the brief flowering of the cosmos before the long winter sets in. Let this knowledge not depress you, but inspire you. The universe will not always be habitable. The opportunities for life and consciousness are limited, but they exist now, and you are part of them. Your existence is improbable and precious, a brief spark of awareness in an ocean of time. What you do with that awareness, how you spend your brief moment in the cosmic story, is up to you. The questions will still be there tomorrow. The mysteries will still be there. The cosmos will continue to exist, whether or not you understand it, whether or not anyone understands it. But tonight, you have traced its history from the first fraction of a second to the present. You have contemplated timescales that dwarf human comprehension. You have connected your own existence to the grand sweep of cosmic evolution. That is enough for one night. That is enough for any night. Let the vastness of the universe be a comfort. Now, let the billions of years before your birth and the trillions of years after your death frame this moment, this breath, this heartbeat. You are here now, alive and aware, made of ancient atoms, carrying forward the story that began before time had meaning. The universe made you possible. It is still making you possible, with every photon of starlight that reaches your eyes, with every atom that participates in your chemistry, with every moment that unfolds from the moments before. Rest now. The cosmos has you. It has always had you. It always will, in some form or another, even after the atoms that currently compose you have dispersed and recombined into other forms. Matter is neither created nor destroyed. It is transformed. You are a transformation of matter, that has been transforming since the Big Bang. You will continue to transform after you are gone. The universe does not waste anything. It recycles everything. You are part of that great recycling, that endless transformation, that cosmic dance of matter and energy through space and time. Sleep well beneath the ancient stars. Dream of the first light igniting in the darkness. Dream of atoms forging in stellar cores. Dream of the long chain of events that brought you here, improbable and beautiful and real. Tomorrow the universe will still be there, still expanding, still cooling, still evolving. But tonight, let it simply hold you. Let the questions rest. Let the wonder remain, soft and warm, a companion for your dreams. The Big Bang happened. You happened. Both are true. Both are wondrous. Both are part of the same story. The only story there is. The story of everything becoming what it is. You are part of that becoming. You have always been part of it. You always will be. Good night. The cosmos is dreaming, and you are part of its dream. Or perhaps you are dreaming, and the cosmos is part of yours. In the end, there may be no difference. There may only be the dream, and the dreaming, and the great unfolding that contains them both. Rest now. The story continues. It always continues, and you are part of it, forever and always, sleeping and waking, dreaming and wondering, from the first moment to the last, and beyond. Good night.